Stars shape the universe in ways that are easy to underestimate. They create light, heat, and the elements that make planets possible. Yet among them exist stars so enormous that even our sun appears insignificant. These are the cosmic giants, stars that push physics to its limits and reveal how extreme stellar evolution can become. To understand these colossal stars, we must begin with something familiar. The Sun is a stable yellow dwarf star with a diameter of about 1.4 million kilometers. More than 1 million Earths could fit inside it comfortably. For billions of years, nuclear fusion in its core has converted hydrogen into helium, producing the energy that sustains life on Earth. Despite its size, the Sun is modest compared to other stars scattered across the Milky Way. Many stars are born far more massive and burn their fuel at a much faster rate. These massive stars live shorter, more violent lives and evolve into forms that dramatically exceed the size of our Sun. As massive stars age, they expand into red giants. This transformation occurs when hydrogen in the core is depleted and fusion shifts outward, causing the outer layers to swell. A red giant can grow hundreds of times larger than the Sun, engulfing nearby planets if they exist. For the most massive stars, this expansion does not stop at the red giant stage. Instead, they evolve into red supergiants. These stars represent one of the largest stable forms a star can take. Their outer layers are loosely bound and extend across vast distances, while their cores burn heavier elements at extreme temperatures. One of the most well-known red supergiants is Betelgeuse, located in the constellation Orion. This star is so large that if it replaced the Sun, its surface would extend beyond the orbit of Jupiter. Its mass and size cause constant instability, with material slowly drifting away into surrounding space. Stars like Betelgeuse represent a transitional phase near the end of stellar life. Their immense size comes at a cost as they rapidly consume their remaining fuel. This leads inevitably to collapse and explosion events that shape the chemical evolution of the galaxy. These giant stars challenge our intuition because they appear calm from a distance, yet internally they are among the most violent environments in the universe. Their existence sets the stage for even more extreme stellar monsters that exceed everything we have discussed so far. Beyond red supergiants exist stars that reach the absolute extremes of stellar physics. These objects are known as red hypergiants, and they represent some of the most massive, luminous, and unstable stars ever observed. Their size, luminosity, and mass loss rates push the boundaries of what a star can physically sustain. Red hypergiants form from stars born with enormous mass, far greater than most stars in the galaxy. From the moment they ignite nuclear fusion, they burn through their fuel at a staggering pace. Their lifetimes are extremely short in cosmic terms, often lasting only a few million years before catastrophic collapse. As these stars age, their outer layers expand to unimaginable scales, while their cores begin fusing heavier and heavier elements. Hydrogen gives way to helium, then carbon, oxygen, and beyond. Each stage releases less energy, causing instability throughout the star. The balance between gravity and radiation pressure becomes increasingly fragile. One of the most famous red hypergiants is Canis Majoris, located thousands of light years from Earth. This star is so large that if placed at the center of the solar system, it would extend far beyond the orbit of Jupiter. Its surface is chaotic, with massive convective cells and violent outflows of material. Canis Majoris is losing mass at an extraordinary rate. Powerful stellar winds eject enormous quantities of gas and dust, forming complex nebulae around the star. This mass loss is a sign that the star is nearing the end of its life, as gravity struggles to hold the star together. These hypergiants are not stable objects. Their shapes fluctuate, their brightness changes, and their outer layers can detach entirely. The instability is so severe that astronomers believe some hypergiants may collapse directly into black holes without producing a visible supernova explosion. The existence of red hypergiants raises important questions. How can a star grow so large without tearing itself apart? What physical processes regulate their expansion and delay their collapse? These questions remain active areas of research in modern astrophysics. Red hypergiants represent a brief but crucial phase in stellar evolution. They act as cosmic furnaces, producing heavy elements that will later be scattered across the galaxy. Their violent deaths enrich interstellar space with the raw materials needed for future stars, planets, and eventually life. As extreme as red hypergiants are, they are still not the largest stars ever identified. Beyond them lies a category of stars that challenge even these immense scales, setting the stage for the largest known stellar monsters in the universe. Among all known stars, there are a few that redefine what size truly means. These stars are so large that standard comparisons fail, and only entire planetary systems can be used as reference points. They exist at the upper edge of stellar possibility, where gravity, radiation, and instability are locked in a fragile balance. One of the most extreme examples ever identified is Stephenson 218, a red supergiant located deep within the Milky Way, near a dense star cluster. Its estimated radius exceeds 2,000 times that of the Sun, placing it among the largest stars ever measured. If Stephenson 218 were placed at the center of our solar system, its outer surface would extend beyond the orbit of Saturn, swallowing Mercury, Venus, Earth, Mars, and Jupiter with ease. The sheer scale of such a star challenges intuition and highlights how different stellar environments can become. Stars of this size exist only briefly. Their immense volume is matched by extreme instability. The outer layers are weakly bound and can be stripped away by stellar winds, pulsations, and radiation pressure. Over time, the star continuously sheds material into surrounding space. Inside such a star, nuclear fusion operates in layered shells. Each shell burns a different element, progressing toward heavier elements as the core evolves. The energy output struggles to support the vast outer envelope, making collapse inevitable once fusion can no longer counter gravity. Measuring stars like Stephenson 218 is extremely difficult. Distance dust and surrounding stellar environments introduce uncertainty. Astronomers rely on infrared observations and stellar modeling to estimate size, luminosity, and mass. Even small errors can translate into vast differences at these scales. Despite these uncertainties, the existence of such enormous stars is well supported. Their role in galactic evolution is profound. They act as factories for heavy elements and powerful sources of energy, shaping nearby interstellar space through radiation and stellar winds. When stars of this magnitude reach the end of their lives, they do not fade quietly. Their collapse can trigger supernova explosions of extraordinary power, dispersing newly forged elements across vast regions of the galaxy. In some cases, the core may collapse directly into a black hole. Stephenson 218 represents the extreme limit of stellar growth. Its existence forces astronomers to refine models of star formation stability and mass loss. It stands as a reminder that the universe is capable of producing structures far larger and more violent than everyday experience suggests. The lives of the largest stars in the universe end in events as extreme as their existence. These stellar monsters cannot fade quietly because their enormous mass ensures a violent conclusion. Once nuclear fusion in the core can no longer produce enough energy, gravity takes control and collapse begins. As the core collapses, it compresses matter to extraordinary densities. Temperatures rise rapidly, and fusion reactions cease in fractions of a second. The inward fall of material rebounds, violently producing a shockwave that tears through the star. This moment marks the birth of a supernova. A supernova releases more energy in seconds than the Sun will emit over its entire lifetime. The explosion blasts stellar material into space at incredible speeds, forging heavy elements such as gold, uranium, and iron. These elements are scattered across the galaxy, becoming part of future stars, planets, and living organisms. Not all massive stars explode in the same way. Some collapse so completely that the shockwave fails to escape. In these cases, the star disappears almost silently, leaving behind one of the most extreme objects known as a black hole. Black holes formed from stellar collapse inherit enormous mass and intense gravity. The region surrounding them becomes distorted as space-time bends inward. Matter that drifts too close forms a glowing accretion disk, heating to millions of degrees before crossing the event horizon. In some cases, the collapse leaves behind a neutron star rather than a black hole. These objects pack more mass than the Sun into a sphere only a few kilometers across. Their density is so extreme that a single teaspoon of neutron star material would outweigh a mountain. The death of massive stars reshapes their surroundings. Shockwaves compress nearby gas clouds, triggering new waves of star formation. In this way, destruction becomes creation, continuing the cosmic cycle. These explosive endings also influence the structure of galaxies. Supernovae regulate star formation rates, drive galactic winds, and enrich the interstellar medium with heavy elements. Without these violent deaths, the universe would be chemically simple and lifeless. The most massive stars therefore play a dual role. They are both architects and destroyers, shaping the universe through their brief but powerful lives. Their deaths mark not an end, but a transformation of matter, energy, and structure on a galactic scale. The largest stars in the universe play a role that goes far beyond their dramatic appearance. Without these cosmic giants, the universe would look very different, and life, as we know it, would not exist. Their immense power shapes the chemical foundation of planets, atmospheres, and living organisms. At the beginning of the universe, only the lightest elements were present. Hydrogen and helium dominated, while heavier elements did not yet exist. The first generations of massive stars changed this through nuclear fusion in their cores, where lighter elements were transformed into heavier ones over millions of years. When these stars ended their lives in supernova explosions, they released these newly formed elements into surrounding space. Carbon, oxygen, silicon, iron, and many others were scattered into the interstellar medium, forming the raw material for future stars and planetary systems. Planets form from disks of gas and dust left behind by earlier generations of stars. Without heavy elements, rocky worlds could not exist. Iron forms planetary cores. Silicon builds crusts, and oxygen shapes atmospheres. Water itself depends on elements forged inside massive stars. Even the chemistry of life traces back to stellar giants, carbon, nitrogen, and oxygen. The basic building blocks of biology were created inside massive stars and distributed by their violent deaths. Every atom in living organisms was once part of a star far larger than the Sun. Massive stars also influence where and when new stars form. Their radiation and shock waves compress nearby gas clouds, triggering star formation in some regions while suppressing it in others. This regulation shapes the structure of galaxies and determines where habitable systems may arise. Without the presence of massive stars, galaxies would evolve slowly and lack complexity. Star formation would be inefficient, chemical diversity would remain limited, and planetary systems would be rare. The universe would be darker, colder, and far less capable of supporting life. The cosmic giants therefore act as engines of complexity. They create the elements, regulate star formation, and seed galaxies with the materials needed for planets, oceans, and living systems. Their brief, violent lives are essential to the long, quiet existence of habitable worlds. Understanding these stars allows us to understand our own origins. The atoms in our bodies, the planet beneath our feet, and the air we breathe all trace back to ancient stellar monsters that lived and died long before the Sun was born. When we look at the largest stars in the universe, we are not only witnessing extremes of size and power, we are seeing the engines that shaped everything that came after them. These cosmic giants lived brief, violent lives, yet their influence extends across billions of years, reaching even into our present moment. The Sun appears calm, stable, and predictable because it belongs to a later generation of stars, formed from material already enriched by ancient stellar monsters. Without those earlier giants, the Sun would lack the elements needed to form planets and complex chemistry. Every comparison between the Sun and stars like Betelgeuse, VY Canis Majoris, or Stephenson 218 reveals how narrow the range of conditions is that allows long-lived, stable systems. Massive stars burn too fast, expand too far, and collapse too violently to host lasting planetary environments. Yet, without these unstable stars, there would be no stable ones. They act as cosmic forges and recyclers, breaking down simple matter and rebuilding it into the ingredients required for complexity. Their explosions seed space with metals, dust, and energy that allow smaller stars and planets to exist. The largest stars therefore represent a paradox. They are hostile, destructive, and short-lived, yet they make life possible elsewhere. Their deaths clear space, reshape galaxies, and prepare the universe for quieter, more enduring systems. Modern telescopes continue to refine our understanding of these stellar monsters. By observing them in infrared radio and optical wavelengths, astronomers can track mass loss, instability, and internal structure. Each new observation pushes theoretical models closer to explaining how such enormous stars can briefly exist. As we expand our reach deeper into the galaxy and beyond, we may discover stars even more extreme than those known today. Each new giant will test the limits of physics and reveal how flexible the rules of star formation truly are. The story of space monsters is therefore not only about scale, it is about origin, transformation, and connection. From the hearts of colossal stars to the atoms inside living beings, the universe is linked through stellar evolution. Understanding the largest stars helps us place our own existence into context. We are not separate from these cosmic giants. We are the result of them. Matter forged in extreme stellar cores now forms worlds, oceans, and life. In the end, the most enormous stars ever discovered remind us that creation and destruction are inseparable forces in the universe. The space monsters may vanish quickly, but their legacy shapes everything that follows.